Hello, this is 2.4, section 2.4, graphing polynomial function. So now we're going to graph. Objectives is behavior of the polynomial function, and then y-intercept for polynomial, x-intercept for polynomial, and then multiplicity of the effect of the x-intercept, what happened to multiplicity, and then graphing the polynomial function overall. So characteristics of the polynomial functions. To begin our discussion on graphing polynomial functions, we are going to discuss the end behavior of the algebraic functions. So to describe end behavior, we use a notation from the following chart. So when x goes on negative infinity, which means x approaches a negative infinity, and then the interpretation means to the left of the end of the graph. Okay, so which means when you have a plane, right? Yeah, so this is a negative infinity of x, and this is a positive infinity, okay? So that's what we're talking about, okay? And this is the x, okay? Then this is the f of x, which is, this goes to the positive infinity, and this goes down to the negative infinity, okay? So this I explained in the table. So when x is approached to the positive infinity, which is the right end of the graph, which is this, and then f of x is negative infinity, which is this one, and f approaches negative infinity, and the graph is pointed at the downward, and then f of x is infinity, f of x approaches infinity, which is the graph is pointed upward, which is this one. So we have a previously studied linear quadratic function without the mentioning the word end behavior, but the end behavior was always controlled by the leading coefficients, so which is very, very important. So leading coefficients. So linear function with a degree of 1 can always be written in the form of f of x equal to mx plus b, where the leading coefficient is m, and then either the positive or negative because of n going positive direction or negative direction, okay? So we got the constructed graph, so this will be a have a graph in here. So this is actually the up, isn't it? And then graph of the negative 4/9 plus 2/3, which is this going down, isn't it? So using our notation and behavior of the g of x equal to 4x minus 6 of the linear function of degree of 1 is a positive leading coefficient, okay? So when x is approaches the negative infinity, which is going down here, x is going here, and the graph is actually going down, isn't it? So negative infinity, which means x goes to negative infinity, f of x also goes to the negative infinity. When x goes positive infinity, and then goes up, isn't it? So f of x goes up positive infinity. But when you look at so that's what they explain here. And then for the f functions, okay, so when x goes to negative infinity, and then f of x goes up, isn't it? So positive infinity, okay. X goes positive infinity, it goes down, right? So f of x goes negative infinity, okay. All right, that's what they say here too. So we must realize that this will be the end behavior of the every line with a negative slope for the leading coefficient. So this will continue to the true for the every polynomial odd degree and the negative leading coefficients. So now we have a 2. So this is a leading term, which is the leading coefficient is 2, and then the degree is a 2. Okay, so when you have an even degree, okay, so the which is a quadratic function, it goes up, isn't it? So when x goes to the positive infinity, and then f of x goes to positive infinity too. And then x goes to negative infinity, and then it goes up to f of x also goes the positive infinity. So either ways, x goes f of x goes to positive infinity. On this time, when x goes negative infinity, which is down, which is f of x goes to the negative infinity. When x goes to the positive infinity, and also down too, so f of x also goes to the negative infinity. Okay, so parabola, actually the end behavior go the same direction. So using our notation, the end behavior of the f of x equal to 2x squared minus 4x minus 1, a function of the degree 2 with a positive leading coefficient can be as x goes positive or negative infinity, f of x goes always a positive infinity. So both sides going up. And then when you have a negative 2 as a leading coefficient, which is when x goes to positive or negative infinity, f of x always go to negative infinity. So this will continue to be true for the every polynomial with even degree and negative leading coefficients. Okay, so in general, we can describe and behavior of the polynomial function as follows. So degree is the odd and even and odd, which is the leading coefficient, which is a sub n, right? If that's a positive, the graph gonna be the forms of this. So up and down, okay? And then the odd and negative, which is this gonna be this is down, but this is kind of past infinity. And then even for the positive, which is it goes up, and for the negative it goes down. Okay, so that's what they say here. So determine the end behavior. F of x is negative x to the 4. So we only need to take the leading coefficient. Okay, so a sub n is negative 1, less than 0, and then degree is a 4. So in behavior means, for the example 1, which is we have to use this, which means it's going to be the both sides down. Okay. Determine the end behavior of this one though. So this is it, right? So a sub n is a 2, and then degree is a 3. So positive degree of 3, this one, isn't it? So it means down on left, and then up on right. So when x approaches the infinity, and then f of x also goes to infinity, x goes to negative infinity, f of x goes to negative infinity for this case, okay? What if the polynomial function is in factor form? So determine the end behavior, but we need the leading coefficient, right? So we take the 2, we take the 1, x, okay, 1x actually, and then from here is a square, so you square the x is x squared, and then you got 4x here, so multiply all together, so I get the 8x to the 1, 3, 4. So this is it. So a sub n is 8, leading coefficient, which is a positive, and then the degree is a 4, which means when x goes so yeah, this one is going up for the both case, right? So x goes to infinity, f of x goes to infinity, x goes to negative infinity, and then f of x goes also still infinity. Example 4, which is a factor form too. So take the 2x, there's no actually the multiplicity, right? So negative 1 and x multiply together. So 2x times negative x times x is a negative 2x cubed. So a sub n is negative 2, which is less than 0. And then degree is 3. So this means what? This side's down, this side's up, isn't it? So when x goes to infinity and f x goes to the negative infinity, x goes to negative infinity, and f of x goes to positive infinity. So now that we can determine the end behavior of the polynomial function, so we will begin the process of finding key points of the polynomial function, namely intercepts. We are going to continue with the same 4 example for which we discussed end behavior, but now we will determine the y-intercept. Just as in linear and quadratic functions, find the y-intercept, let the x equal to 0. Alright, now finally example 1. Determine the y-intercept. So in order to y-intercept, good thing is y-intercept means x is always 0. So what do? Plug it in 0. So negative 0 to the 4 minus 10 times 0's cube minus 28 times 0 squared minus 6 times 0 plus 45. So everything cancels out except the 45. So y-intercept is 0 and 45. Example 2. Determine the y-intercept 2. So same thing. You use a 0 for x and then plug it in. 2 times 0 cubed minus 3 0 squared minus 3 times 0 plus 2. So everything cancels except the 2. So 0 and 2. That's the y-intercept. Notice that if the polynomial function is not factored, the constant will be always the determine the y-intercept. The same thing. But if there is not it's a factor form. So same thing. You plug in 0. So 2 times 0 negative 3. 0 plus 1 squared, 4 times 0 minus 1, which is 2 times negative 3, 1 squared, and negative 1, right? So it's going to be positive 6, isn't it? So, yeah. So, which is a 0 and 6. G of 0 for the next example. So, same thing. 2 times 0 minus 3, 1 minus 0, 0 plus 5. So I got negative 3 times 1 times and 5, negative 15. So 0 and negative 15 for the y-intercept. So again, we are going to continue with the same for example, but now we will determine the x-intercept, which is going to be the zeros, okay? If we recall earlier sections of this chapter, finding x-intercept by letting f. Okay, that one is not okay, so I don't think I agree with that. Hold a second. So let me see what it says. Okay, so this is not right, okay? So which means f of x set equal to 0, okay? Not the x equal to 0. Okay, sorry about that. That's a mistake. Okay, it's the same question as finding the 0 of the function. So only differences between the 0 of the polynomial function and x-intercept is that we can have non-near complex numbers as zeros. But we will not yield x-intercepts. Only real number 0 will be the x-intercept. Okay, so if it's complex 0, it's not going to be the x-intercept at all. So example 1, determine the x-intercept this time. So which is, yeah, this is not factoring form or factorable, okay? So what I do is, I need to find the possible rational zeros, which is plus minus a factor of 45 and plus minus, oh, we already have plus minus, right? So we just say factor of 1. So plus minus 1 and then 3 divides, right? And then the 5, of course, then 9, and then maybe 15, and then 45, right? Okay, so those are the possible rationals here. Okay, so starting with this, so synthetic, negative 1, negative 10, negative 28, negative 6, and 45. So we have at least one positive real 0 for that case. Drop negative 1, negative 1, negative 11, negative 22, negative 39, negative 39, negative 45, oh, negative 40. Oh, yeah, we got 0 already. So this is a 0. Okay, so now I have negative x cubed minus negative 11x squared minus 39x minus 45. Okay, so now from here, I'm going to use the negative one this time. So let's see what happened. Okay, so drop the negative 1, 1, negative 10, 10, negative 29, 29, negative 16, which is not going to be a 0, so negative 1 is not going to be 0. So starting negative 1, negative 11, negative 39, negative 45, I'm going to use another possible negative 0, okay? So negative 1, 3, negative 8, 24, 4, negative 15, and 45. That's a 0, right? Okay. So this is another 0, which means this is degree of 4, right? So we just need to find the 2 more 0, but that's possible because it's going to be negative x squared minus 8x minus 15. So negative x squared minus 8x minus 15 equal to 0, okay? So I think this is factorable, okay? So I want to say pull down negative x squared plus 8x plus 15 equal to 0, which is x plus 3 times x plus 5. That's another, okay? So as the x-intercept, which is going to be the 0, right? So zeros you're going to get as 1 and negative 3, and this is another negative 3 and negative 5, okay? Which is going to be the x-intercepts too. So as x-intercept, you might want to put that as 1, 0, negative 3, 0, and negative 5 and 0, okay? So you don't have to put the negative 3 twice. Now, in example 2, determine the x-intercept too, okay? So same thing. Let's find the possible rational 0 as a plus minus of factors of 2 from this 2, okay? And then factor of 2, but from this 2, okay? So which is you got plus minus 1 and 2, 1 and 2, which is going to be 1, 2 and a half. Oh, that's nice. It's not that long. So 2, negative 3, and 2. So I know you're going to get the 1 real 0. So it's going to be a 1. Okay, so starting here. Drop the 2. 2, negative 1, negative 1, negative 4, negative 4, negative 2, which is not going to be a 0, so 1 is not going to be 0. So 2, negative 3, negative 2, and 2, negative 1 divided, drop 2, negative 2, negative 5, 5, and 2, negative, yay, we got 0, okay? So negative 1 is a 0, which means you can just put out as 2x squared minus 5x plus 2 equal to 0, which is factorable, isn't it? So 2x and x, and then 2 and 1 with a negative, isn't it? Yep, equal to 0, right? So another 0 will be 1/2 and 2, okay? So those are the excited steps, okay? Which means negative 1, 0, half 0, and then 2 and 0. So those are the excited steps. Alrighty, example 3. Determine the x-intercept for this. Okay, the good thing is this is already the factor form, so we don't have to factor. So where the 0 comes from? X minus 3 equal to 0. X plus 1 equal to 0. But this 0 repeated twice. Okay? 4x minus 1 equal to 0. So we should have a full 0 because it's degree of 4. So 1, that'll be a 1, 2, and 1. Added up will be 4. But the 1, 0 is a multiplicity 2. So we have to just write once. Okay, so x equal to 3. X equal to negative 1, so for x is a 1/4. And the x-intercept, 3, 0, negative 1, 0, and 1/4 and 0, okay? Example 4, determine the x-intercept for that, yeah? So we have a, set the all linear factor equal to 0. So at 3 divided by 2, 3 over 2. At x both sides, x equal to 1, and then subtract 5, x equal to negative 5. So those are the 0, okay? Now x-intercept, 3 over 2, 0, 1, 0, and negative 5 and 0. So as a final step, before we can graph polynomial function, we must discuss the role multiplicities play when the graphing polynomial functions. So the multiplicity of each 0 will affect what a graph does x-intercept associated with that 0. So consider the function p of x equal to x minus 1 times x plus 4 squared. So zeros are 1 and negative 4, but negative 4 has a multiplicity 2. So therefore the function x-intercept is 1, 0 and negative 4, 0. The x-intercept 1, 0 came from the 0 of the x equal to 1, which is a multiplicity 1. Let's see what happened to our function near the x-intercept of 1, 0. Especially with the sign of our function value. So consider x equal to 0, x equal to 2. So when you plug it in 0, you got a negative number. And then if you use a 2, plug it in, you got the positive numbers. So with the input close to the x-intercept of the 1, 0, the value of the function changed the sign from the negative on the left to the positive on the right because x minus 1 changed the sign. So the result is that the graph will go from the below of the x-axis as it passes through the x-intercept. At the x-intercept, we will describe the behavior of the going from one side of the x-axis to the other as going through the x-intercept. So x-intercept negative 4, 0 came from the 0 of the x equal to negative 4 of the multiplicity 2. So let's see what happened to our function near the x-intercept of negative 4, 0, especially with the sign of our function value. So if you use a number from the negative 4 to negative 3, which is a negative 4 right in the middle. So if you use a negative 5, it's going to be negative sign. Negative 3 is going to be negative, which means it won't cross the negative 4, right? So with the input close to x-intercept of the negative 4, 0, the value of the function remained negative in both left and right of the negative 4 because of the factor x plus 4 squared will always be positive because of the even exponents. The result is that the graph stays on the same side of the axis both before or after touching the x-intercept. So we describe this behavior as a bouncing up off of the x-intercept. So in general, if the x-intercept comes from a 0 of the odd multiplicity, the graph usually goes through the x-intercept. And then if the x-intercept is about the odd multiplicity, okay? So and the even multiplicity as a 0, the graph bounces off of the x-intercept. So just a touch, okay? So for this case, which means it's going through, and this means it's just touch. Okay? Alright, graph of the polynomial functions. We now have all building blocks needed to graph polynomial function, but before we begin, there are two details about the polynomial graphs that needed to be mentioned, okay? So first, the domain of the every polynomial function is all real numbers, negative infinity, infinity. So the graph of the every polynomial function will be one continuous curve. So secondly, the curve with a smooth curve without any sharp points. So let's begin with the graph of the four examples discussed throughout these sections. So example 1, f of x equal to negative x to the 4 minus 10x cubed minus 20x squared minus 6x plus 45, which is we factor as this form. So we need the factor, okay? So y-intercept was 0, 45, plug it in 0 here, 0 here, and 0 here, right? And then x-intercept, which is, we already solved it too, right? So we got the 1, 0, negative 3, 0, and negative 5. And then end behavior, which is from the negative x to the 4, which is when x goes infinity or negative infinity, it all go down to the negative infinity, okay? So let's put down all the 0 first, okay? So y-intercept is about here. So let's say 0, 45. And then the 1, 0, yeah, the scale, I don't really care about scale this time, okay? And then this is a negative 5 and 0. And then there's a 1, 0 here. So the end behavior is going to be the down, down, right? So it's going to be a down from the kind of this, okay? Yeah. And then multiplicity of the negative 5 is a 1. It's a cos, which is going to the negative 3. But negative 3 has a multiplicity 2, means it's a bouncing back to go to the y-intercept. And then going down to the another x-intercept. Yeah, so you have a graph of this, which is, do you see the similar to this one? Which is I already graphed for you guys, okay? All right, the example 2. The graph of the g of x equal to 2x cubed minus 3x squared minus 3x plus 2, which is we have those factors. So y-intercept, plug it in 0, 0, 0 here, get 0, 2. X-intercept is negative 1, 0, 1 half, and then 2, 0, which is everything is a multiplicity of 2, which is going through on the x-intercept. And behavior, because the 2x cubed is the right side is going up and the left side is going down, okay? So that's what exactly they're telling me here, okay? All right, so let's think about the graphing. So we have negative 1, 0, half 0, and then about 2, 0. And then Q, which is you got one side's up and other side's down, right? But everything is going through, which is y-intercept is 0, 2, okay? So going through, okay? Yeah. It's similar, but you know, the down and up is a little bit different, okay? Example 3, f of x equal to 2x cubed minus x plus 1 squared times 2x minus 1. So yeah, when you multiply out, y-intercept is 6 comes out, x-intercept is 3, 0, negative 1, 0, and 1/4 of 0. And then it's a degree of 4 with a positive, so both sides goes up, okay? So if I put the y-intercept somewhere here, 0, 6, okay? And then there's a 3, 0, negative 1, 0, and 1/4 0. So this is up, isn't it? So which is it's gonna be up, but the multiplicity of negative 1 is touch, okay? So touch going back to the y-intercept, and then everything the other 3 and the 1/4 is a multiplicity 1, so going through. Yeah, so I get the similar one right here. Alrighty, so process for the graphing polynomial function can be described as follows. So on number 1, plot the y-intercept, and then plot all the x-intercepts, determine the end behavior by the leading term, and then draw the graph from the left to the right using the multiplicity to determine the behavior of the x-intercepts. So odd multiplicity going through and even multiplicity bounces off. Okay, so let's do the problem here, okay? So I have a factor form, isn't it? So which means for the y-intercept, I use x equal to 0, okay? So out of the 0, which is 0 square of 0 plus 3 square, 0 minus 4, which is going to be a 0. So y-intercept is a 0, 0. X-intercept set equal to 0 for the out of x. So x square of x plus 3 square, x minus 4. So x equal to 0, but multiplicity 2, and then x equal to negative 3, and then multiplicity 2, x equal to 4, multiplicity 1, okay? So there are 2 bounds off and then 1 going through. And behavior, I need to multiply x squared 2, and this x squared to another x here. So it becomes x to the what? 5th, isn't it? So a is 1, which is a positive, right? And then the degree is a 5, which is we're going to have this to this, okay? So from the 0 we have, so there's a 0, 0, and then there's a negative 3, 0, and there's a 4, 0. Okay, so which means as a 0 is touch, negative 3 is touch, right? So it goes up, 4 is across, going back to the 0, and then the bounce off, whatever that happened, and bounce up to the negative 3, 2. So that's all. That's for the graph. Example 5. Graph of f of x equal to negative x cubed plus 3x minus 2, okay? So x-intercept, which is, we have to find it, okay? So, and the y-intercept is easy, right? So I'm going to switch this to, okay? So y-intercept is f of 0, right? So negative 0 cubed plus 3 times 0 minus 2, which is negative 2. So 0 and negative 2. And then x-intercept, we need to set this one equal to 0, which is negative x cubed plus 3x minus 2. But we have to find the possible rational 0 because it's not factorable, okay? It's going to be the plus minus of factor of 2 and then factor of 1, which is plus minus 1 and plus minus 2 for this case. So if I use a negative 1, but 0, there's no x squared, so use a 0 for x squared, 3 negative 2. And then I am using 1. The good news is I already have 0, yay! So this is 0, which means I have a negative x squared minus x plus 2 equal to 0. Factor the negative x out, x plus x square minus 2, which is negative x plus 2 times x minus 1. So we get the another zeros are negative 2 and the 1. So 1 repeated, right? So okay, so which is the zeros are x equal to 1 as a multiplicity 2, x equal to negative 2 is multiplicity 1, okay? And behavior is a negative, a sub n is negative 1, which is less than 0, and then the degree is 3. So this is a case of this to this, okay? So we got 2 zeros, so negative 2 and then 1. So it's going to be this and this. And then the negative 1, 1 is touch, right? Because it must be 2. And then minus is negative 2. And then going back to here. Okay. Alright. I think that's all. Okay. Alrighty. Okay, so that's all for this sections. Okay. Thank you for listening.